Alright, in this video I'm going to do a few examples of solving exponential equations. And three examples here. On the first one, we're not going to have to, we can just kind of use a little clever trick, I think, to get our value exactly. To get our exact values in part B and C, though, we're going to have to use some logarithms. But for part A here, we've got 1 over 27 equals 9 raised to the 5x minus 7. The thing that sticks out to me in this problem is that 27 is a power of 3. And I know it's 1 over 27, but in the denominator, 27 is a power of 3. 9 is also a power of 3. So I'm going to rewrite 27 as 3 cubed. 9, we can write that as 3 squared. And then we still have our 5x minus 7. Well, on the left side, I'm going to bring my denominator upstairs by writing it as 3 to the negative third. And then on the right side, again, since these are in parentheses, we multiply. So 2 times 5x would be 10x. 2 times negative 7 would be negative 14. And now, since we have like bases, we can just set the exponents equal to each other and solve. So we would get negative 3 equals 10x minus 14. Well, I can add 14 to both sides. That would give me 11 on the left side and just 10x on the right side. And now I can simply just divide both sides by 10. And it says my solution would be x equals 11 over 10. Okay, so nothing too bad there. However, if you look at the second example, 8x equals 15, well, you know, I don't know how to write these with an equivalent, sort of base like we did in the last example. So what we do at this point is the trick to get, eventually I want to solve for x, and I want to get the x away from being the exponent. And, again, in general, this is an exponential function. You always want to think about what's the inverse, what undoes something. And the inverse of an exponential is a logarithm. So I'm going to take a logarithm of both sides. You can use any logarithm you want. Most of the times we're going to use log base 10 or the natural logarithm so that we can put it in a calculator. So I'm just going to take the natural logarithm of the left side. Well, hey, that means I have to take the natural logarithm of the right side as well. Okay, and don't get thrown off, the natural logarithm of 15, that's some number. I always, I don't turn these into decimals because then you're approximating, and I want to keep them exact. So remember this property that says if you have exponents, you can bring them out front. And this is the whole point of using the logarithm in the first place. So on the left side, we would have x times the natural logarithm of 8 equals the natural logarithm of 15. And well, if we want to solve for x, we can just simply divide both sides by that number, the natural logarithm of 8. And on the right side, we'll just have ln of 15 over ln of 8. And to me, hey, that's our solution. So again, you can always plug this into a calculator if you want a nice decimal approximation. But I'm just going to leave it right there. It's exact, and hey, that's what we need. So one more example here. We've got 4/5 raised to the x equals 6 raised to the 1 minus x. Well, exact same thing. I see variables upstairs as exponents. The way I'm going to get those away from being exponents is by throwing logarithms onto both sides. Again, you can use any type of logarithm you want. You obviously have to use the same one on each side. I'm just going to use the natural logarithm again. So we have the natural logarithm of 4/5 raised to the x equals the natural logarithm of 6 raised to the 1 minus x. No particular reason I switched from brackets to parentheses. They're all the same to me. So the x would come out front on the left side, and we'd have natural logarithm of 4/5. On the right side, 1 minus x, that's our exponent, so that's going to come out front. Notice I keep it in parentheses, times the natural logarithm of 6. And at this point, this to me is just a linear equation. Again, don't be thrown off by the logarithm. It's just a number. It's just a number. What I do is I get rid of all the parentheses. So on the right side, ln of 6, again, is just a number. You could pretend it's sitting out front. And in either case, we have to distribute it to both things inside the parentheses. So ln of 6 times 1 is just ln of 6. then we'll get minus x times ln of 6. And now what I'm going to do is I'm going to put my x's on the same side. So I'm going to add x times ln of 6 to both sides. So on the left side, we would have x times the natural logarithm of 4/5 plus x times the natural logarithm of 6. On the right side, we have just ln of 6 left over now. And, if this was a linear equation, well, it is, but if we had nicer numbers, say 4 and 6, we would just add 4x and 6x. But, I don't know, ln of 4/5 and ln of 6, well, I'm not too sure. You could always put it in a calculator, but the idea is, algebraically, you can just factor out the x. And then we have ln of 4/5 plus ln of 6. On the right side, we still have ln of 6. And now if we want to solve for x, we can simply divide both sides by this quantity, ln of 4/5 plus ln of 6. If I do it on the left, I've got to do it on the right. So ln of 4/5 plus ln of 6. And on the left side, we'll just be left with x, which is going to be what we want. On the right side, we have ln of 6. We could even combine notice our logarithm in the denominator, because we have addition, and that means we can multiply. So we would take 4/5 times 6, which would give us 24/5. And at this point, again, you can't combine ln of 6 over ln of 24/5. You can't combine that into a single logarithm. But again, if you wanted a decimal approximation, you could plug everything in. But to me, this is now a nice exact answer. And we're finished.